Hello everyone. So far we've been looking at principles related to the design of an amplitude modulated optical sensor. We've been looking at some case studies related to gas spectroscopy. Then we went to looking at a pulse oximeter and then optical time domain reflectometer. Now let's see if we can put all of these together and whatever principles we learned, we can put that to use to serve a practical application. Let's say you are an engineer that's taking a requirement from a customer and trying to meet that requirement. How do you go about designing such a sensor? Okay, so that's what we're going to focus on in today's lecture. So let's say this is the requirement, right? So we previously saw a guest lecture by Dr. Anish Bekal, in which he was talking about flue gases such as carbon monoxide, nitric oxide, sulfur dioxide, and so on. And these are pollutants, and we need to be monitoring these fairly closely. So you've been asked to design an optical sensor to monitor the level of NO from an extracted sample at the rate of 10 measurements per second. So the absorption cross section of NO is given in this plot. This is basically the transition cross section as a function of wavelength for both NO and CO, but NO corresponds to these transitions over here. There are multiple transitions in that region. So essentially we've been asked to assume that you can pick one of those transitions for absorption spectroscopy, and you can assume that the transition is actually a Gaussian shaped transition centered at a wavelength of 1100 nanometer with a spectral width of about 6 gigahertz and a peak cross section value, a peak transition cross section value of 0.6 in 10 power minus 25 centimeter square. And you're supposed to it's mentioned this is an extracted sample, so you can actually have the sample in a gas cell whose length is 0.5 meters. So we ought to go and design such a system. So let us go ahead and try to do that. Okay, so what we've been told is this is actually an amplitude modulated sensor. So you can start with a laser, right? And that is going to be sent through this gas cell. Right, whose length L is 0.5 meters, right? And then whatever is coming through that gas cell, you want to pick it up with the optical receiver. This is what we had been looking at previously. And in this case, we said we typically to pick up this absorption accurately, we use what is called differential absorption spectroscopy. So let's go ahead and try to look at that. So you use differential absorption spectroscopy. So what do we do in differential absorption spectroscopy? We send a light beam through this gas cell at a wavelength corresponding to the peak of resonance for an absorption event, and then we measure what is the power that's coming through, and then you go off to, you tune the laser. Suppose you have the ability to tune the laser, so you tune the laser so that it goes off resonance, and then you make one more measurement. right? So, so essentially, if you're measuring the power that's transmitted at the resonant wavelength, let's call this PR, that's going to be equal to P0 of R. So that's actually the power that's incident on the gas cell, and then you undergo some losses. So only a fraction of that power is actually going to go through absorption. So let's actually put all these external losses as eta external, and then it's going through an absorption in the cell that's given by Beer's law. So you have sigma r is the transition cross section, multiplied by n is the concentration of the gas, which is what we want to measure, multiplied by L, which is the length of the gas cell, right? And so that is at the resonant wavelength. So this is at resonant wavelength, which has been given as 1100 nanometers, right? So that's what we have been told, that we are interested in picking up nitric oxide in this gas cell. So so we are actually looking at a resonant wavelength of 1100 nanometers. So then what do? You go off resonance at non-resonance lambda. So this is basically, we call it at lambda r, non-resonance at some other wavelength, right? We don't know that wavelength yet, but we actually, that's one of the things that we need to find out. What is the non-resonant wavelength that you need to go to? Okay, so let's say we go to this other wavelength, and this is the incident power at the other wavelength. Let's assume that you're moving off by such a small value of wavelength that the other losses don't change within that. Then you go minus sigma, exponential minus sigma nr, that's the transition strength at this non-resonant wavelength, multiplied by n multiplied by L, right? So that is what we do in absorption spectroscopy. So let's go back to this question and see what we've been asked to do. So what we've been asked to do is, we've been told that, okay, you can use differential absorption spectroscopy, and we've been asked to figure out what should be the non-resonant wavelength that you will choose, such that the absorption extinction is 20 dB. Okay, so that is what we want to do next. Okay, so let's go back here, and let's go to a fresh page. So what you've been asked to do is, you've been told that when we look at this transition at a wavelength of 1100 nanometers, so we are looking at sigma, which is typically expressed in centimeter square per molecule, right? We've been asked to assume that it's actually a Gaussian shaped transition. So it's going to go look something like this, and we've been told that the this wavelength is the resonance wavelength, and at that resonance wavelength, this is been given as 0.6 multiplied by 10 power minus 25 is the strength of the transition. So that's the transition cross section. Now you have to go to some non-resonant wavelength, so such that we are actually seeing a drop of 20 dB in the absorption cross section. So we say, okay, you go down 20 dB over here, that's actually a factor of 100, right? And that where that meets this transition curve here, that is going to be our lambda NR. So it could be either over here or on the other side, right? So you can call it lambda NR1 or lambda NR2 or whatever, right? So those are one of the wavelengths that we could pick to go to, and then we will essentially do the non-resonant. So what we've been told is that the transition spectrum is Gaussian shaped, right? So is shaped as a Gaussian. So we can write the this basically this spectrum we can represent as e power minus lambda lambda minus lambda r the whole square divided by 2 times delta lambda square, where delta lambda would correspond to the RMS width of this transition. So this here would correspond to delta lambda, right? So so we've been told that this non-resonant wavelength is picked such that lambda NR minus lambda square, if we do this, then this will actually be corresponding to a factor of 0.01, right? So that's corresponding to 20 dB in terms of absorption, right? So that's 20 dB down, right? So if we do the math, so we can basically rearrange all these terms and try to get a expression for lambda NR. Lambda R we know. Delta lambda is something that we've been told. So we have been told that delta nu, according to the question, is 6 gigahertz. Okay. So if you know delta nu is equal to 6 gigahertz, can you figure out what is delta lambda? Well, you can say that delta nu would correspond to nu correspond to C over lambda. So delta nu corresponds to minus C over lambda square delta lambda. So we're not interested in the sign, but we are interested in only the magnitude. So so we can just write it as C over lambda square delta lambda. That is actually given as 6 gigahertz. So you can rearrange terms and you can say delta lambda now corresponds to lambda square, which is basically 1.1 in 10 power minus 6, the whole square, divided by C, which is 3 into 10 power 8 multiplied by 6 gigahertz, right? So that will correspond to delta lambda, which is in nanometers. So if you do the math, what you will find is this corresponds to 0.024 nanometers, right? So this delta lambda, this width, the spectral width in terms of wavelength is given as 0.024 nanometers. So which we can actually plug into this expression here and get an expression, get a value for lambda NR, right. So, to do that we will have to just rearrange some terms. So, if you take the inverse of this, so this will be basically this value equal to ln of 0.01. So, you take the negative of that, so negative goes over there, and so then you take the numerator and move it over there. So, that corresponds to 2 times delta lambda square multiplied by ln of 0.01 whole negative, and then you take the square root of that and then move the lambda r on the other side, and that is how you can get lambda nr. So, if we do all of that, what we will find is lambda nr equal to lambda r, and so it could be plus or minus, it does not matter, because you can get either one of these values. So, lambda nr plus or minus root 2 delta lambda multiplied by minus ln of 0.01 the whole root. So, that is point to the power of 0.5. Okay. So, you can do this, and then you can find out what is the shift in wavelength that you need to do to get to the non-resonant wavelength, such that the absorption drops by a factor of 100, right. That is what we are trying to get to. So, if you evaluate this you will find is this lambda r we have been told is 1100. So, 1100 plus or minus, if you do the math, you will come to about plus or minus 0.073 nanometers, or rather 73 picometers is what you need to move so that you can get down by a factor of 100 as far as the absorption transition cross section is concerned. So that is essentially one thing that we have been asked to find out. So let us go back and see what else we need to do. So, that is the non-resonant wavelength. Then you have been asked to ask this question, what type of laser will you use for this application? Okay. And then you have been given certain parameters, and you have been told, you have been asked to figure out what is the drive current required to achieve 1 milliwatt output power. Okay. So this we discussed previously, right. So, if you want to do absorption, differential absorption spectroscopy, you need a source which is much smaller compared to this delta lambda, right. So, you ideally need a delta function, but let us say it's of a finite width, but as long as the width is much smaller compared to delta lambda, then that will be good for this application. So, delta lambda we found out is 0.024 nanometer, which corresponds to 6 gigahertz in terms of spectral width, right. So, you need something whose you need a laser whose line width is much less than 6 gigahertz. So, we can safely, so let us basically look at the B part. So, we say we will use a laser whose line width is far less than 6 gigahertz. So, one standard laser that we know whose line width is much less than that, so that essentially works with a single longitudinal mode. What laser is that? That is actually the distributed feedback laser. So, you can actually go for a distributed feedback laser, which is in short it is called a DFP laser. So, what are we talking about? Just to refresh our memory, we are talking about a semiconductor laser with a PN junction and then right. So, there is something that looks like this. Now, only thing we have in a DFB laser is that you actually have some periodic corrugation near the active region, such that it provides distributed feedback all along the length of the laser, and then that is actually giving us emission from this. So, you have a high reflective mirror. So, you have a highly reflective mirror over here and a partially reflecting basically a cleave on the other side. So, then what you get out is light from this aperture over there, right. So, that is what we saw before. Now, when it comes to the output power from such a structure, we saw that the output power is determined by the rate at which you have these carriers that are injected inside into that structure, and what matters is the number of carriers that you inject beyond a certain threshold value. So, that is what is actually contributing to stimulated emission in the cavity. So, we saw previously, so P naught corresponds to h nu over q multiplied by there could be some there is a something called an internal quantum efficiency, which means that is the fraction of recombination events that results in emission of a photon, right. So, that is what we call as eta int multiplied by I minus I threshold, right. So, whatever current the rate at which we are sending in charges, basically I over q. So, but the current beyond this threshold value is what is going to contribute to this significant output power. So, basically we are looking at P out as a function of current, and then it is going to be going through spontaneous emission up to a certain point, and then you start having stimulated emission, and you start overcoming the losses in the cavity, and then you can get this output power. So, we have been asked to figure out what is the current at which we are able to achieve 1 milliwatt of power. So, we have been told that P naught we should take as 1 milliwatt. Eta int is given. So, if we go back here, so we have been told that the internal quantum efficiency is 0.9, and then you also been told that the internal loss corresponds to 20 per centimeter and a mirror loss of 5 per centimeter. So, let us see if we can put all of those together. So, so eta int is given as 0.9, your threshold current is given as 30 milliamperes, okay. So, that we know, and then of course, that is actually the power that is generated within the cavity, but the power that is escaping, a fraction of power that is escaping from the cavity is given as eta external, which is actually given by the output mirror loss alpha m divided by the internal losses plus the total mirror losses where this back mirror is almost 100% reflective, so we don't expect much losses there. So as far as the cavity is concerned, only this mirror is providing the losses. So you can write this as alpha m over alpha int plus alpha m. The denominator denotes the total losses in the cavity. So this is given by this is given as 5 over 20 plus 5. So if we do the math, is 5 over 25 is 0.2. Okay, so we have all these values, and we know what nu is. Nu is corresponding to C over lambda, and lambda is supposed to be 1100 nanometer as far as this application is concerned, and Hc over q is actually a constant. So this you can write it as Hc over q multiplied by 1 over lambda, right? And Hc over q is a constant that is given by a value of 1.24 if you make the calculation. If you, h is the Planck's constant, c is the velocity of light in free space, and q is the charge of an electron. So if you plug all this in, so you will find that this corresponds to 1.24 divided by lambda, as long as lambda is expressed in terms of micron. Okay, so we have all these values. So now we can plug everything back into this expression, and then we can actually find an expression for I. So if you just rearrange all these values, you will find this corresponds to I equal to I threshold plus P naught, which is 1 into 10 power minus 3 multiplied by lambda in micron. So that's actually 1.1 divided by 1.24. Okay, that accounts for these terms, and then 1 over eta int, which is 0.9, and eta external, which is 0.2, right? So if we do all this calculations, so what you will find is this corresponds to 30 plus roughly it will come to about 5 milliamps, right? So this will correspond to about 35 milliamps. Okay, so you need a drive current of 35 milliamps. So that's somewhere over here. Let's say this is 35 milliamps, so that you can get an output power of 1 milliwatt at 1100 nanometers, which is what we are going to use in our setup basically, right? So this is what we are going to use to probe this gas cell, and we will assume that we are able to get the same amount of power. So this is actually given as 1 milliwatt. We will assume that this is also 1 milliwatt. There's not going to be a significant change in power when you tune from one wavelength to another. And let's say this laser, we are able to tune that much by just changing the current or temperature, okay, at which it's operated. So we are able to get both the resonant and non-resonant wavelength with the same laser. Okay, so that's how we're going to do this spectroscopy. So let's go back here, and let's actually find out what else we need to be doing. So the next thing you've been told is that the background losses in the above setup is 90%, and we are asked to assume the same power level. That's what we talked about just now, as just 1 milliwatt, and the maximum gas absorption is 10%. Okay, so you've been asked to assume it's a maximum gas absorption of 10%, so if that's the case, then question is what is the minimum power level expected at the receiver using appropriate mathematical expression. So we already looked at some of those expressions. So let's just go back here and let's see how this is going to work out. Okay, so this is basically part C. Maybe I'll just use the color. So part C, this is what you've been told. Let's actually just try to visualize what we have been told. So let's say this is actually a function of lambda. You are looking at the power that is coming through the gas cell. Okay, so we know that you're initially starting with 1 milliwatt of power, right, from the laser, but we've been told that 90% of that is lost to external whatever attenuation mechanism. So 90% of that, let's say over here, so 90% is lost, right? So what we have remaining is only 10% of that. So that's actually 0.1. Let's say this is expressed in milliwatts. So we have a value of 0.1. And within that, what we've been told, so that is actually the power level that we have at the non-resonant wavelength. So the non-resonant wavelength, we have negligible absorption. So we can say that the non-resonant wavelength, the output is going to be corresponding to 0.1 milliwatt. And so that is actually the background. And then as you approach the resonant wavelength, it's going to go through an absorption, right? So this is actually lambda r, and we have used some other wavelength here as our non-resonant wavelength, at which almost there is negligible absorption. Okay. Now what we've been told is this absorption corresponds to 10%. Maximum absorption corresponds to 10%. Okay. So so let's actually try to express that. Okay. So we've been told that PR we know is P naught R, and then eta external multiplied by e exponential of minus sigma r n into L, right. So this factor of exponential minus sigma r n into L, maximum of that is going to be 10%. Okay. So it is at that maximum absorption you're going to have the minimum power, right. So what we've been asked to figure out is what is the minimum power that we are expecting at the receiver. Okay. So that is going to correspond to the resonant wavelength, right. So so let us now see if we have all these values to figure out. Now we know this is actually 1 milliwatt, that's what you are starting with, and eta external is actually the fraction of power that's available for absorption. So 90% is lost. So the fraction of power that's available for absorption is 0.1. This is some people find it a little tricky to understand. So we say 90% is lost, right. That's what the question is saying. According to the question, we are losing 90% of the power, right. 90% background is background losses. So then if we say that is the background loss, then people say that is eta external is equal to 0.9, which is obviously wrong, because 90% is lost. So what is remaining is actually 10% of the incident power. Okay, so you have to be very careful about that part. And then of course we have been told that the maximum absorption corresponds to 10% of whatever power is available. It's 10% of 0.1 milliwatt in this case, and so that is, no, it's not 10% of 0.1. So this is the other important thing. So this is actually 10% is the deviation that we are having from this from the power level of 0.1 milliwatt. So this factor corresponds to actually 0.9. Okay, so 90% of the power is remaining after this absorption, after this maximum absorption. Okay, so if we just do the math there, so what we will find is this corresponds to 0.1 milliwatt, and 90% of that is basically 0.09 milliwatt. Okay, so that's what we are looking for. That's the minimum power that we expect at the resonant wavelength, right? That's the minimum power that we expect at the receiver. So now we need to build our receiver such that it's capable of picking up this minimum power level. Okay, so let's now move on, and let's see what else. I think we are now ready to design our receiver. So let's just go back and see what we need to be doing next. So what type of photodiode would you use for the above application? Okay, and then of course you're given certain parameters for the photodiode. What should be the absorption width to achieve a responsivity of 1 ampere per watt? Okay, so let's look at that now. By the way, we are talking about picking up 90 microwatts of power, and we are saying the responsivity needs to be only in the order of 1 amp per watt. So that already tells you that you don't need an APD photodiode, because you have so much power already. So you can go for a PIN photodiode. But then mind you, the wavelength that we are using is 1100 nanometers. So what material would you use to pick up 1100 nanometers? And when we look at that material, we find that to detect 1100 nanometers, we can consider silicon, because silicon has responsivity typically from 400 nanometer to close to about 1100 nanometers, but that's right at the band edge, right? That's the edge of the absorption. So it falls off in terms of responsivity very sharply around that wavelength. So we will say that maybe that's not as suitable, right? So what we can go for instead is indium gallium arsenide, which typically exhibits fairly good responsivity from about 0.7 or 700 nanometers all the way to 1600 nanometers. So that is what we are choosing. We are choosing an indium gallium arsenide PIN photodiode for this particular application. Okay. So now the question is, if you are using a PIN photodiode, let's actually draw the structure here. So we have a very thin P region, a very thin N region, and a relatively long I region, and we have electrodes on either end of that, and then we are looking at optical power being incident on this. According to so what we've been asked to do is figure out the width of this absorption region. So this width W, such that you can support a responsivity of 1 ampere per watt. Actually 1 ampere per watt is not possible in indium gallium arsenide at 1.1 micron. I'll tell you why. So there was a mistake there, so we should correct that. Okay, but let's look at responsivity. Responsivity is given by eta q over h nu, right? And that can be, of course, we saw before, can be written as eta times lambda, as far as lambda is expressed in microns, divided by 1.24. The same thing, it's basically hc over q corresponds to a value of 1.24 as long as lambda is expressed in microns, where eta itself is given by 1 minus Rf. That's actually the fraction of power entering into this structure. The structure can have a facet reflectivity of Rf, and then it has a photoelectron conversion efficiency. It's given by zeta multiplied by the amount of power that's absorbed, which corresponds to 1 minus e power minus alpha. Alpha corresponds to the absorption coefficient in the medium multiplied by the width. Okay. Now we've been asked to assume that RF is anti-reflection coated. So RF is 0. Okay, we can assume RF is 0, and zeta we've been asked to assume that for this material it's 0.95, and we've also been given alpha at this wavelength. We've been told is that corresponds to 10 power 4 per inverse centimeter. Okay, so we can actually plug all those and find out eta. Okay, but eta, where do you find that from? Eta, we'll have to get it from this expression, because we know lambda is 1.1 micron. Okay, so if you try to do that, and if you actually try to get 1 ampere per watt responsivity, right? So eta multiplied by 1.1 divided by 1.24. If you do the math over here, you will find that eta is actually 1.24 divided by 1.1, which is a value greater than 1. Now, can eta be greater than 1? Cannot be, because this is actually a fraction, zeta is a fraction, and this is also a fraction which has a maximum value of 1. So eta has to be a number that's less than 1, okay, which obviously is not satisfied over here. So contrary to what's asked, we'll actually assume that you've been asked to get a take a responsivity of 0.7 amp per watt. So if you say, okay, that is our target responsivity, then eta is going to be given by 1.24 multiplied by 0.7 divided by 1.1, which is a value of 0.79. Okay. Now this we can take over here. So this entire thing has to be equated to 0.79, So, if we rearrange terms, then we can actually find out W, which is going to be given by inverse of alpha, negative inverse of alpha, which is 10 power 4, and then you have a ln of 0.79 divided by zeta, right. So, that is actually and there's going to be a 1 minus factor. So, that will basically be ln of 0.17, and this is in centimeter because alpha is expressed in terms of centimeter. So, 1 over 10 power 4 centimeter is micron. So, you can just evaluate this, it will work out to be 1.78 micron. Okay. So, that is actually the width of the absorption region that is necessary to support a responsivity of the PIN photodiode of 0.7 amp per watt. Okay. Now, let us just go back to the question again and see what else we have been asked to do. So, you have been asked to identify and quantify the possible noise sources in the above setup. Assume that you have OPA 656 for the transimpedance amplifier, and you also have a 10-bit ADC with a range of 0 to 1 volt. OPA 656 noise characteristics are given. En is actually the voltage noise current density that is given by this curve over here. It is actually high at low frequencies. This is basically the 1 over f noise, and then it becomes white noise, whereas In is basically flat across. So, that just given us 1.3 femtoamp per root hertz. So, so we are supposed to use this for building our transimpedance amplifier. So, let us go back to this. Let us take a fresh page once again, and let us try to do a noise analysis. So, to do the noise analysis, we need to say, okay, let us actually get a picture of our receiver circuit. So, you have a certain power level that is incident, and we already figured out what is the minimum power that we are getting. So, the minimum power what we determined earlier corresponds to 0.09 milliwatt. What is the maximum power that we are going to have? That corresponds to this value, right, the non-resonant, the value that we will get at the non-resonant wavelength, that corresponds to 0.1 milliwatt. So, we can say that this corresponds to 0.09 to 0.1 milliwatt. That is the kind of input powers that we are expecting over here. And then we will take this photocurrent that's generated over here, IP corresponding to this input power, right, and then we'll go through a transimpedance amplifier, and then we will take the output of that and go to a analog to digital converter, and then it's available as digital samples for further processing and display. Okay, so that is the receiver design that we are looking at. Now the question is, what sort of transimpedance gain you need, and then what is the corresponding noise that you accumulate at the receiver. So to do that, we need to understand that this ADC it's given as 0 to 1 volt. So with the maximum power that you have here, it should be such that it's filling the ADC. Okay, so so that's what we want to first find out. So you need to have a transimpedance gain such that this this power that's falling on it's incident on the photodiode, it's generating a certain photocurrent, right? So let's look at this maximum power at receiver is 0.1 milliwatt. At 0.1 milliwatt, what is the photocurrent that we are expecting? So the corresponding photocurrent is at a rate of 0.7 amp per watt. That's what we looked at the previous section. So that corresponds to 0.07 milliamperes, right? And this photocurrent now needs to be converted to a voltage so that it fills the ADC. So the transimpedance gain that we require in this case is going to be 1 volt divided by 0.07 into 10 power minus 3, right? So that's going to be so that's amperes. So that's if you do the math, take the inverse of this, this will work out to be about 14.3 kilo ohms, right? So that is the transimpedance gain that we need. And 14.3 kilo ohms is small enough that we could possibly support with one TIA stage itself. Especially it's not just the transimpedance gain but also the bandwidth requirement. So in our case, our bandwidth requirement right, we are required to do only 10 measurements per second. Okay, that is the requirement. So we don't need much more than 10 hertz. The information that we want to capture is not beyond 10 hertz type of frequency, right? So so we can possibly, that's low enough bandwidth requirement, so we can possibly get all this transimpedance gain in one OPA 656 stage itself. Okay, so we will say that we have a transimpedance amplifier with 14.3 kilo ohm as the feedback resistance. Okay. If we have that, then the question is what are the noise sources that we expect over here, and can we quantify those noise sources? Now, first of all, we do realize that when light actually is incident on a photodiode, the arrival times of the photons are random in nature. So we have what is called the short noise, that's actually Poisson distributed arrival time. So we have what is called the short noise that is present over here. So and then while it's getting amplified, it will essentially accumulate thermal noise in the receiver, and then also the op-amp whose noise characteristics we just saw, the op-amp will also contribute to the noise. So those are the major noise sources, and of course we can also have quantization noise in the ADC. Let's just neglect that for a second now, and let's look at all these other noise sources. So to look at the other noise sources, we can basically say this the noise is En RMS at the output. Okay, I think we are using En for the voltage, noise, current density of our of the op amp. So let's actually say this corresponds to En0, okay, but we are interested in the RMS voltage there. So En0, we previously saw, if we just add all those, each of those is an independent random variable. So the variance of each of those, the noise power basically correspond to each of these processes. Those are going to add, and then we will and then we'll have to take the square root of all, the summation of all of those. So that will give us the RMS value, right? So we saw that this would correspond to RF multiplied by root B whole root of 4 kBT divided by RF is the feedback resistance of the TIA, plus we are using a PIN photodiode, so we don't have any of these contributions due to noise contributions to avalanche processes. So it's simply 2Q multiplied by IP, right? And then you have a noise. So we are essentially capturing the noise current density, right? So then we have the noise current density corresponding to an op amp. So the variance is IO op amp square, plus you have E op amp square divided by RF square, because we are once again tracking the noise current density, right? So let's try to quantify all of these numbers. So RF, we've been told it's we just figured out it's 14.3 kilo ohm. So we substitute that over here. So we will get a value of something the order of 1 into 10 power minus 24 watts for that for the thermal noise component. And then if we look at the short noise component, that is if you evaluate, this will be 2.24 into 10 power minus 23. And then IOA, that corresponds to the current noise density that's provided by the op amp, that is in the order of femtoamperes per root hertz. So if we evaluate that, that will come to about 1.7 multiplied by 10 power minus 30. So that's quite negligible compared to all these other numbers. And then EOA, so this is actually an interesting point that we need to keep in mind, right? So when we talk about voltage noise current density, we see that we need only 10 hertz, right, from a transimpedance amplifier. If we look at that, we will essentially get about something the order of it's 75 nanovolt per root hertz, okay. So that is actually something that we need to keep in mind. If you are able to go to a larger frequency, especially if you are able to go beyond 10 kilohertz type of frequencies, then you can possibly reduce this. If you just, because you need only 10 hertz bandwidth. So if you shift your detection to higher frequencies, you could possibly incur much lesser noise. How do you shift the frequency of operation? Well, one common method that we saw in one of the previous lectures is using lock-in detection. So instead of doing all these measurements at DC, what if you are able to do this measurement with modulated light instead of doing with continuous wave light. If we can actually do intensity modulated light, then especially at a frequency say 10 kilohertz or above, then you can possibly bring down the voltage noise density. Okay, we will come back to that at a later point, but at this point we are assuming that we are doing it in baseband, which means that we want to look at the value at 10 hertz, okay, which is 75 nanoamps per root hertz. So we plug that into this and divide that by RF, we will get a value of 2.75 multiplied by 10 power minus 23. So among these we clearly see that these are your primary noise contribution. So it's first of all, it's a short noise limited type of receiver. It's not thermal noise limited receiver, because the amount of power that we are expecting is relatively on the higher side. If the same thing was in the order of nanowatts, then the short noise component will be very low. You will have a component because of this thermal noise, and you may have to even go for an avalanche photodiode in that case, right? But this is actually a case where we are looking at short noise limitation. But what we are also seeing is, because of the 1 over f noise, because of the frequency at which we want to do this detection is on the low frequency side, you are actually having a relatively high contribution from that. Okay, so that is actually from the op amp itself. Okay, so those are the kind of things to consider. Now let's just go back and see what else we've been asked to figure out. So then finally we've been asked to figure out what scheme would you adopt to achieve the best possible minimum detectable limit. Provide a schematic diagram of setup and appropriate mathematical expressions. Okay, so let's actually try to do that. So while we are at this, let's actually also try to figure out what is the total noise power that we have in this case. Okay. And to figure out the total noise power, so we need to actually evaluate this part, all these components first of all. So we can just say that the total noise current density that we have here, it corresponds to square root of all these addition of all these things. So this is corresponding to square root of you add these two components, that corresponds to 5 into 10 power minus 23. So it's square root of 5 into 10 power minus 23 and square root of B, right? So where B is the noise bandwidth of your receiver, right? Actually so since we are multiplying that by root B, you don't call this the noise current density, that's actually the total noise current itself. Okay, so now the question is what is B? Okay, so so B, requirement is only 10 hertz, but when you do a design using its transimpedance stage, we know that B corresponds to the F3 dB of your transimpedance amplifier. So, if you look at the F3 dB of your transimpedance amplifier, which is corresponding to the noise bandwidth of the receiver that we are looking at, that corresponds to root of the gain bandwidth product divided by 2 pi RF, and then there are multiple components, capacitance contributions. So, CF plus CD plus C op amp and all that, right. So, that is capacitance corresponding to all of this. Now, CD, C op amp and all that, let us say that corresponds to about it is typically in the order of 1 picofarad. So, that is fine. So, what about CF? Now, in this case, we want to limit the bandwidth. So, we want to limit the bandwidth. We already know that RF corresponds to 14.3 kilo ohm, right. So, we need to constrict the bandwidth so that you do not accumulate a lot of noise, right. You need to basically low pass filter your receiver, whatever the received signal is, right. So, you want to limit that, and when it comes to limiting this CF, if you look at typical values of CF that you can pick up, so that you can put this into sort of like a PCB, right. You will find that this corresponds to about 1 microfarad, okay. And we know that the gain bandwidth of OPS 656 is about 400 megahertz, okay. So, if you plug in all these values, you will find that B actually corresponds to a value of 66.7 kilohertz, okay. And your requirement is only 10 hertz, but you are actually having to deal with a B or value of 66.7 kilohertz. That is primarily because of the fact that of course, you can increase RF so that you can constrict B, but you do not have an opportunity to do that because you already filled your ADC with this value. So, you cannot go any more beyond that. So, the only choice is to increase CF, but that actually when you are getting it as a circuit in a PCB, that may be limited, right. So, that is where this limitation we have considered as 1 microfarad is concerned. If you, for example, go to 1 millifarad, then you can actually get to a much smaller value, but to get to 1 millifarad you need a fairly bulky capacitor. So, it is not compatible typically with a PCB, okay. So, that is the constraint that we see. So, because of this, when you actually look at this is actually the total noise current that we have looked at, so if you look at if you evaluate this, you will find that this is root of 5 into 10 power minus 23 multiplied by 6.67 into 10 power 4. Okay. If we do the math, so that corresponds to 30 and it's another 3, so about 33, so 34 into 10 power minus 19. So, So you can take it as 10 power minus 18, so you can get 10 power minus 9 out, and multiplied by roughly about 340. So square root of 340 is going to be something around 19 into 10 power minus 19, right? So that's in so that's about that's in amperes. So that's the total noise current that we are expecting. Okay, and of course, if you want to look at the voltage corresponding to that, you have to multiply that by RF, and so that if you do so multiply by RF, which is 14 into 14 kilo ohms, then you'll probably get something in the order of microvolts. Okay, so we'll come back and do that later. So that is actually the total noise that we are picking up from this. Now, in the last part, we've been asked to figure out what is the kind of minimum detectable limit that we have. Okay, so let's look at that. How do you define the minimum detectable limit? Now, from our expressions before, we can actually figure out what is n as a function of PR, right? So, if we just rewrite that expression, so the gas concentration, which is a number of molecules per cubic volume, that is n. N can be written as, when we rearrange all those terms, n can be written as minus sigma r multiplied by L, and then ln of PR, that's the transmitted power measured at the resonant wavelength, over the transmitted power that we measure at the non-resonant wavelength. Okay, so that's it is to that we get this gas concentration. If you plot this, let's say we are plotting this, we are trying to figure out what is the concentration based on a measurement of PR. If you look at this, all of these are like constant values. So PNR, for example, for our case, we said is 0.1 milliwatt, right? And sigma R we know that is 0.6 in 10 power minus 25. L we know is 50 centimeters, right? So this is 50 centimeters. That is 0.6 into 10 power minus 25 at the resonant wavelength, right? So all these are constant, and only PR changes. PR changes according to changes in changes in the gas concentration. So when you have a higher concentration, the value of PR is lower, and conversely, if it's low concentration, PR is higher. How high can PR be? Well, when you have the limit of n tending to 0, right, then PR will become PNR. Right, when that's essentially, go back and look at this, we say if there is no absorption, then this will actually just be a flat line. So PR is going to be equal to PNR, right? And then of course we are saying as concentration increases, PR decreases. So it's basically an inverse relationship. So I can write it, I can plot it with respect to inverse of PR, and if we do that, then what we see in this case is it should be a sort of a linear relationship. Okay. So the question is, what is the minimum detection limit that we have? So the minimum detection limit would be somewhere over here. Let's call this minimum detection limit. And what is that limited by? Well, that's limited by the uncertainty in your power measurement, right? So this is actually the minimum power change, right, that can be measured reliably. Okay. So that will essentially limit the lowest concentration that you can pick up. That actually limits the that determines the MDL value. Okay. So let us actually to determine this, we will say that we can that corresponds to delta PR change or delta N change with respect to delta PR. So we can differentiate this expression. So you can, if you differentiate that expression, you say dN over dPr. What is that value? Well, if this is basically ln of PR over PNR, but PNR is a constant. So when you do that differential, you will find that it's got basically it comes to 1 over PR. So this will be nothing but minus 1 over sigma R L multiplied by PR. Okay. So if we want to now find out the minimum detection limit MDL corresponds to dN, right? That's the smallest value change in the concentration that we can pick up. That corresponds to 1 over sigma R L PR multiplied by the dPr. So now the question is, what is dPr? dPr corresponds to the uncertainty, which is essentially the noise power that we have. Okay. So this is actually the RMS noise that we have, that's incident, the noise equivalent power that we consider as incident on the photodiode. Okay. So let's go ahead and determine dPr. So dPr is going to be given by root of the noise, the total noise power divided by your responsivity. Okay. And the total noise power, if we calculate, that will correspond to what we have over here, 5 into 10 power minus 23 multiplied by B. So, actually I made a mistake here. So, this should be 1.82. So, that is actually the total noise current, that is the RMS noise current. But when we talk about noise power, that will be square of that. So, that will become 3.4 into 10 power minus 18 watts. Okay. So, when we want to do the calculation of the equivalent optical power, so this is actually the electrical power, right. So, if you want to look at the optical corresponding optical power, then we can say basically dPr, well, we already put it there. This is the we have the corresponding electrical power root of that. Why are we taking a root? Because we are interested in the current, the noise current, because what is happening in the detector is the optical power is getting converted to a photocurrent. So, we need to take the root of that to take the noise current and basically divide that by the responsivity. So, that is what we have here. This is 1.82 multiplied by 10 power minus 9, that corresponds to the noise current, divided by the responsivity, which is 0.7 amp per watt. So, that will correspond, that will give us the equivalent change in minimum change in power that we can detect. Okay. So, that will be if you do the math, it will correspond to about 2.6 nanowatt. Okay. So, now we can plug this over here. So, we know all the other values. So, this is 2.6 into 10 power minus 9 divided by you have 2.6 into 10 power minus 25 multiplied by L, which is 50, multiplied by PR, which is in the limit of n tending to 0, because that's the limit that we are interested in. It just corresponds to PNR, which is 0.1. Just verify that. Yeah, that's PNR is 0.1 into 10 power minus 3. So, if you do that math, it will come to so this is 50 times 0.1 is 5, multiplied by 0.6 is 3. So, 2.6 divided by 3 is about 0.9. 0.9 multiplied by this 10 power minus 28, and that's 10 power minus 9. So, it's 10 power 19. So, that's 10 power minus 19 molecules per centimeter cube, right. So, that is the minimum detectable limit. And so, what does it correspond to in terms of the actual concentration? So, if you do dN over N, if you do, then you can actually figure out what is the actual the minimum concentration in terms of parts per million, and this will work out to be roughly, if you take the ratio of 10 power minus 9 and 10 power minus 3, that corresponds to something in the order of parts per million. So that is the kind of level that we are able to achieve with this technique. Now, question really is how can we improve this? right? What can we do to improve this? Well, we know already that one way of improving it, that's what we discussed previously, is by this potentially we can reduce this component. How do we reduce this component? We can go to a higher frequency of operation. Instead of doing this in DC, you can actually go to a higher frequency. So instead of in your setup, we say we have this laser, we need to drive some current. So if you drive it, actually let's say we are driving it with some we are driving the current at some frequency FM, okay. Then we have this going through the gas cell, and then whatever is coming back we are taking it into the receiver. This receiver output now, before you just coming off the transimpedance amplifier, you can actually mix it with your with the reference frequency, and then you can actually do lock-in detection. Then you can actually beat it down, because this one is you are expecting some signal around FM. Let's say FM we pick it about 10 kilohertz. Why 10 kilohertz? Well, if you just go back to what has been given for our application, right? So we've been told that you are using an op amp that is having white noise beyond 10 kilohertz. So if you go to this value, then you can actually bring down the noise by quite a lot, right? So that's what we are looking at. So if we do that, then you can reduce the noise that you are accumulating at the receiver, and that's what we are seeing over here. You can reduce this component significantly by 2 orders of magnitude potentially, right? And then you can also through that you can bring down the noise that you are accumulating, and then you can improve. So that if you bring down the noise that you are accumulating there, then you can actually reduce DPR, right? The minimum change in power that you are able to detect from the receiver, and through that you can actually improve your minimum detection limit. So what we are saying is MDL can be further reduced through lock-in detection at FM. In this case, FM could be in the order of 10 kilohertz, which means that in your receiver you can still actually whatever bandwidth over which you are accumulating noise, that noise you will be able to reduce by using a low pass filter over here, right? So you have the low pass filter with a cutoff of 10 hertz, right? So you do the lock-in detection with FM of 10 hertz and low pass filter cutoff at 10 hertz, because that's all the information that you want to get, right? So So, in frequency what we are doing is we have basically FM, right, and we are through this lock-in detection process we are beating it back to baseband, and then we are applying a low pass filter at 10 hertz, and that's all the noise that we pick up. Okay. So, the noise power will also significantly come down. Here we were when we were calculating noise power, we were multiplying this by this value here, right. Now, you do not have to use this value, you can basically use only 10 hertz, and if you use 10 hertz, that is actually a factor of 10 power 4 lesser. So, your noise power will be a factor of 100 because it is coming so the corresponding noise power will also be reduced by that factor. Okay. So, so that is clearly one way of improving the minimum detectable limit, and another way of improving it further is so this is one way, and the other way you can improve it even further is MDL can be further reduced through what is called wavelength modulation spectroscopy. That is, instead of just doing an intensity modulation, what if you are able to modulate the wavelength itself such that you are in this case, so you are doing wavelength modulation spectroscopy like we talked about previously. If you are able to do this at some value FM, right, and then you are able to do this detection at 2 FM frequency, right. So, you have a corresponding intensity variation at 2 FM frequency, right. So, if you lock into that, then you can basically have a zero background. So, essentially you do wavelength modulation spectroscopy where modulation is done at FM, and then you are actually detection at 2 FM. So, if you are doing that, there is negligible background, you do not have any other spurious absorption coming into the picture, then you can possibly get even better improvement or even better value as far as the minimum detectable limit is concerned. Okay. So, that hopefully sort of gives you a feel for all the things that you could do with amplitude modulated sensors. So, that's just a realistic example. So, this is what you need to do. You need to take the requirements from your customer. You need to see what are all the things that you could possibly do. It all finally comes down to how you can handle noise, right, and what we saw was using this lock-in principles is a very nice way of handling noise and achieving fairly low values of fairly high performance, fairly low detectable values. Okay. So, let's stop right there.